The potential field for a charged dielectric sphere. So this is a very similar setup as we did with the charged conducting sphere. So we imagine that we have a test charge at r equal to infinity that is being pushed towards the charged dielectric sphere. So when I'm looking at this, I'm kind of seeing something like this. I have a sphere that looks something like this. And I have charge everywhere. So it's a uniform charge distribution. And then I'm going to be going along this straight line because that's the easiest path that we can do for our line integral. So then I take my test charge. Here's my test charge. And then I'm going to move it to a distance r. Then I'm going to move it to the surface, and then I'm going to move it inside. So when I'm looking at these test charges, I want to calculate what is the height of these guys. So initially we start at point P, and this is a distance r. This is at r equals to infinity. This is little q. This guy is big Q. And you could see here is that we're looking at a point here where little r is equal to big R. And then right in here, we're looking at little r less than big R. We know the electric field of a dielectric sphere. So the electric field of a dielectric sphere is E of R. If we're inside, we get 4 pi epsilon big R cubed into big Q times little r. So it's linear. And then outside, it acts like any other sphere. Oops, yeah, that's right. And then I have r squared here, and then this is q, and this is for r greater than big R. So now we're just going to go right through the calculations, and let's get started with the outside, because we've already done the outside. So here we go. So we're outside the dielectric sphere. And this potential is for R greater than big. I should really be more careful and say that this is between infinity and big R. So let's go do this. So one cannot distinguish between a conductor slash dielectric sphere from the outside. Therefore, they have the same fields. That means both electric and potential. They're exactly the same. So I don't even have to look at what we're going to write because we're going to say, we've already calculated this. So between big R, little r, and infinity, this is going to be VR less than this. Maybe I should write it differently. It's going to be so I'm going to get for little r greater than big R minus V at infinity. This is going to be the negative of the integral of infinity to r of the electric field that we've already know what it is. It's going to be 4 pi epsilon r squared q dr, and we've calculated this already. So this value then becomes plus 4 pi epsilon r big Q minus 0. We knew that. So we know that there are two values. There are two values here. One of the values is that if I'm in the outside, then I have little r bigger than big R, and we know that this guy has to be 4 pi epsilon r q minus 0. And if I'm at the surface, so I'm coming from infinity all the way to the surface here, then we get this relationship right here. And this is what our field looks like right here. So once again, let's draw our picture to make sure that I'm driving this as much as I can. So picture-wise, what have we just calculate? So if I'm looking at my sphere, and what color did I draw? I draw it green. So if I'm looking at my sphere, then this is what I'm seeing. I have a quarter of a sphere. And I'm looking at my potential function here. And I know that this distance right here is r. So now that I have that, I know that I have a uniform charge distribution. So now at this point, we can see here is that the potential function has to look something like this, where it goes to 0 at r equals to infinity. So at r equals to infinity, we know that that's what we call the ground. And this here is just the potential function here. So when I'm looking at this, what we're seeing is that we're climbing from infinity. And if I get all the way to the surface, I get to this point right here. And we say here that then this height right here, if we calculate this voltage, we then say that the voltage height at the surface is equal to 4 pi epsilon big R cubed. But if we only make it to right here, then we know that that depends on the location of little r. So this height is smaller. So then we could then say that this guy is then going to be at some function of r that's going to be 4 pi epsilon little r big Q. So since little r is larger, it's going to have a smaller potential. But as I get to the surface, I would expect that the surface value will be larger. So let's physically think about what are we expecting to see. So what should we expect to see for the dielectric? I think the first thing that we should do is that we should talk about the conductor. So a conductor had a maximum at the surface. So we got to be careful. What do I mean? Maximum height. And that maximum height is, of course, the voltage at the surface. Now, the question is, why is that a maximum? Inside a conductor, there is no enclosed charge or charges that will push back on you. In other words, repulsion. Therefore, the work inside, as we saw, was zero because there was no enclosed charge. But what about the dielectric? This is not true for dielectrics, since there is enclosed charge. That will push back on you. They're definitely going to push back on you. This causes more work. And therefore, in potential language, you climb up higher. So just on physics, we expect that we have to climb up more of the hill because there's enclosed charge. Untrue for the dielectric. So now let's go calculate this. So now we are inside the dielectric sphere. And then this is the potential between 0 and big R. So let's go back and get our initial picture. So if I come back here, I want this picture again, because this is useful. So I could say here is that our initial picture was this guy. So when I'm looking at this guy, the thing that I got to pay attention to is that I always have to come in here and say always remember to start from infinity and work your way in, or work your way inwards. You have to do that. So now let's calculate the potential. So the potential field now has to be something like this. So I know I want to go inside. So I'm going to say this potential field is going to be from 0 to big R. And then the first thing I got to do is that I got to climb all the way to the surface. That means I'm starting at infinity and I got to go to big R. So now I have a potential that has to get me to the surface, which is little r equal to big R. In other words, we have to climb to the surface first. So once I climb to the surface, now I could climb into the surface. So then I'm going to have a second term that now tells me I'm now inside the surface, which will then be between here and there. So I would expect that there's a contribution. So now what I'm going to do is that I'm now going to climb higher inside. And that's because we know that there's enclosed charge. So when I look at these integrals, what am I seeing? I'm seeing I get negative, and I'm going from infinity to R, and this is going to be the field of the outside. And then I have the field that I'm now inside, like this. Now, once again, I know I've said this a couple of times, but it's okay to repeat oneself. These are different, right? These are different fields. So now let's do this. Now note, from 0 to infinity to R, we've already calculated this. So I'm going to come in here and I'm going to say that this guy is going to then be, I'm going to color this. Let's see, how did I draw it? I drew this in green. So I'm going to continue to draw this in green. So I'm going to say this is the contribution from the field from from infinity to big R. Right? So this represents the height at R equals to big R. Now, I'm going to put in that electric field. We wrote that electric field up here. Look at the electric field. I'm going to take this term right here and I'm going to write that in. So inside, I now have an electric field that then reads minus, then I have a constant. And then the integral is going to go from big R to little r, and then I'm going to get R dr. Now, I'm going to color code this because that's telling me about the inside. So this is then going to be the additional height inside that I'm going to have to climb. So now let's calculate this. So if I integrate this guy, then this is what I'm seeing here. I get the exact same term here, right? I'm going to get the exact same term right here. So that hasn't changed. So I'm right here. Now I got to integrate this guy. And when I integrate, I'm integrating a fairly simple integral, which is just a factor of r. The details show that this will then be 4 pi epsilon r cubed q. And then I'm going to get this definite integral to look at 1/2 r squared little 1/2 big R squared. So now you are seeing that this is the outside height. This is now the inside height. So when I put this all together, here's what I'm going to look at here. So if I write this all and I clean this up a little bit, this is what I'm going to see. I'm going to separate this out into two terms. So the first term that we want to look at is that the first term is the outside height, which we just talked about. So this is 4 pi epsilon r, big Q. Now I'm going to bring that term that's positive in, and that's going to give me 8 pi epsilon, big R, Q, and this is a positive value. And then I get an important negative quantity, which is then 8 pi epsilon r cubed q. And then I'm going to put this r squared in black because I want that thing to stand out. Once again, these mean exactly the same thing that I wrote already. So this here is our potential function when I'm between 0 and big R. So our job is to really understand what this means right here. So I want to focus on the purple part of the potential field. So focus on the purple potential field due to the inside. Now let me remind you about Gauss's law. So Gauss's law for dielectric spheres states that the enclosed charge decreases to 0 as r goes to 0. So if I was to look at this picture-wise, you could imagine that I have my sphere here. And what you're seeing here is that if I now plot the electric field, okay, you know what? I'm going to bring this down because I'm out of space. So if I call this axis here the electric field inside, and then this guy right here is R, we know that we have a uniform charge distribution in here. So if I look at what the field looks like inside, we see that this field drops all the way to 0 like that. And again, that is just telling us here is that the enclosed charge goes to 0 as we move in. So now what does the potential field behave inside the sphere as r goes to 0? So if I look at only the inside, then I could say here is the limit as r goes to 0 of the potential term for the inside is then equal to the limit of all of the purple stuff. In other words, I'm going to get, I think it's 8 pi epsilon r, big Q, and then I believe it's 8 pi epsilon r cubed over Q, and then I get that r squared term. Let me double check. Yes, that's it. So I'm taking the limit of all of this, and what you're seeing here is that this term right here, it goes to 0. In other words, this term right here, 8 pi epsilon r q minus 0, this is the maximum additional height climbed from the surface. So if I start to look at this thing, then let's draw the whole thing here. So I'm going to draw this nice and big. Okay, I'm going to draw this nice and big. So I'm thinking, so I want my E field here. So I'm going 1, 2, 3, 4, 5, 6. So now I need 6 here. And this is 6. So then I'm going to say that this guy is my potential field as a function of R. So what does my shell, my sphere look like? It's going to look something like this. There's my quarter sphere right there. So I'm not going to put any charge, but we know this is a charged dielectric. So I'm just going to draw the potential field. Otherwise, I'm right on this curve, because otherwise it's going to be a problem because I won't fit it on the screen. So here we go. This is the distance of R. So when I look at the potential field, I'm really looking at this term right here. This is what I want. Let me copy and bring this down because I'm going to need this. So if I put this here, let me see if I can place this right here. Uh-oh, where did I put this at? Oh, here it is down here. So by the way, I see I have a typo. This should just be as a function of R. That is what I wrote is incorrect. So if I'm looking at this, here's what I'm going to draw. I have the outside field that's going to look like this. And so if I'm looking at this field right here, we agree that this is the potential field right here. And you know, that green's going to really cause problems. So I think I'm going to change the color just so that I could separate it. I'm going to make this yellow instead. So what I know here is that right in here, I know that we're talking about outside the surface. And when I look at this, if I'm looking here, I'm seeing that my potential field between big R, little r, and infinity is equal to this guy, which is proportional to 1 over little r. That's what we're seeing right there. When I have this test charge that's moving in. So now, if I look at this test charge, I'm seeing that this little test charge now has climbed all the way to the surface here. So here I'm at, right here. I'm at the surface right here. So how high? So if I look at that green value, that tells me that I have this height right here. That height tells me that the potential at the surface is then going to be 4 pi epsilon big R into Q. And that's what that outside height means. Now what I'm seeing here is that now I continue to climb. And what we said here is that if I look at what I just wrote up here, we said that the maximum height, so the maximum height inside is this guy here, which then says that the maximum height inside is when r is equal to 0, which is then this 8 pi epsilon big R into big Q. So if I look at this guy, you could see that this is half the size of this value at the surface here. I think that's half. Yeah. So what I'm seeing here is that there's going to be an additional climb. This additional climb says that if I now take my charge and I bring it all the way to right here, all the way to this spot, it has now climbed an additional height from the surface from here to here, right? That's the same height right here. That height then will then be 8 pi epsilon big R over Q. Actually, I don't think I want to put that there. I'm going to bring this over here because I have other plans there. So I'm going to say that this guy is the inside max. Which is equal to that guy right there. That's at r equal to 0. So the reason why I wanted to reserve this is that, check this out. This tells me here that now I have a total height change. So if I look at the total height change, that guy has to equal 4 plus, you know what? I'm going to run out of space, so I'm going to have to do it down below. So then the total height change is then going to be, it's going to be the height to the surface plus the maximum height on the inside. And so if I put these numbers together, this number is the green number. This number is the purple number. And that's going to give me this outside height and then I have this guy right here, which is the maximum height inside. And now all I have to do is add them together, and I'm going to get a value that then reads 3q over 8 pi epsilon r, and this is the total height. So when I look at this total height here, from r equal to infinity, then I could say here is that this guy right here is V total will then be 8 pi epsilon r divided into 3q. That's the maximum height. So now all I'm doing here is that I just got to plot the rest of this. And then I'm going to say here is that then the plot then should be like that. And so if I was to look at this, this is essentially the contribution inside the potential field. So, and if I was to then summarize the whole thing, I would then, I mean, even though we've already written it, but if I clean this up just a tiny bit here, and I'm going to really start with this relationship right here. So then I say here that in summary, the potential field function is then going to be this. I'm just going to write it. It's going to look like this. It's going to say that I have an outside field, and look at the relationship. I'm going to have the outside contribution, so I'm going to get 4 pi epsilon r cubed. Then I get the inside term, which then reads 8 pi epsilon r cubed, and then I'm going to get 8 pi epsilon r cubed q, and then I have this r squared term. If I add those two terms together, then what I'm really getting is that I'm getting this 8 pi epsilon r 3q minus 8 pi epsilon r cubed q r squared. And this is going to be between 0 and big R. On the other hand, if I'm outside, then I'm going to get this as a function of little r, and this is going to be between r less than little r and infinity. This is the potential of a dielectric sphere.